to do or what you'd like to talk about or to see. So the first thing, I mean, there is sort of a global order. The first thing that we can do is to look at material that we didn't manage to cover yesterday. That could either be in the case histories or examples. And I need my that one's not very good. So just to remind you of what we did do. So we started off with the DC resistivity, and the thing that I thought was maybe a little bit novel for people, and certainly I find is very useful, is really putting the DC resistivity problem within the context of charge, and thinking about if you illuminate something, that you've got currents that's going through, it's requiring charges that are built up, and that's really what you're measuring when you're measuring an electric potential surface. We looked at the fundamentals both in with kind of a 2-coil app and a 3-coil app, and tried to show the basics of Faraday's law and Ampere's law, and kind of then morph that into how you do an inductive source survey. A couple of examples, both were connected with water. So one was a time domain experiment that was done in Denmark, and there the geology is such that you've got near surface resistive materials, sands, gravels, and that's overlying clay material. And so that makes a great contrast. If you're looking for a resistor over a conductor, then an EM method is really great because you'll pick up that conductor. And I think maybe one of the things that we really tried to drive home here is that if you're using an EM technique, you're sensitive to conductors. You're basically transparent to anything that's resistive. That's contrast to DC resistivity, in which you have a little bit of extremely resistive material, and you just simply can't go through that. So that's an important limitation for DC resistivity, and you also kind of understand why inductive methods are actually so important. There was a few case histories, both in time domain and, well, yeah, especially in time domain, that we did not cover here, and we could look at those or not. There was one with respect to getting near surface structure to handle to get a better velocity model for seismic. Somehow I don't think that's quite would quite strike a resonant chord, but I don't know, we take a look at that. And then we went to grounded sources. So that kind of combines DC resistivity and inductive sources. Because now you're actually worried about not only current being transmitted through the ground as a DC, but also what's the effect of the wire. And the wire is really important because that's the source of energy, and it kind of propagates through. So you need to take. We showed one example here for grounded sources. It had to do with a long offset time domain EM. The reason I chose that was it's sort of a different scale. So now you're talking about a major region in India. But there's quite a few others that we have, in particular, when you talk about marine EM, to look for hydrocarbons and de-risking. There's also, there's a mineral exploration project, Magdalena, that uses inductive sources and borehole sources and also some grounded sources that we could take a look at. So there's extra case histories that were here. The one thing that really resonated when we went to a couple of other places was the understanding of how a grounded system works when you're in an ocean environment. Because there we get waves that actually propagate up into the air and then go across. It's something that's called the air wave, and it creates havoc with the geophysical data. And it was one of these things that was debated hotly for a couple of years. People were trying to understand, what this thing really is. How do I remove it? What do I do with it? And we've actually got a tutorial that I think explains it very nicely. And the reason that it explains it, I think, nicer than anything else I've seen, is that it gets you out of the frequency domain. It basically provides a movie of what the wavefronts look like in the time domain. And then once you see that, it's like, oh, I got it. I understand. The other things back in here that are I think important, and again, sort of depends upon the audience. There's this combination of DC resistivity signals and electromagnetic induction. I mentioned yesterday that often you do a DC resistivity survey, but maybe you're trying to get the IP signal out of that and the off time. But there's a region of early time in which you're contaminated by EM induction. Traditionally, that's just thrown away. But in fact, you can use that information to as signal and try to find what the electrical conductivity is. So that's kind of interesting, and I think that's new. People tend not to do that, but I think there's opportunities there for people to acquire about the Earth without doing very much extra work in the field. It's just a matter of sampling at a higher rate and sampling earlier. So natural sources, we looked at MT. There's a companion to that, which is flown a lot in the mineral industry. It's called ZTEM. So it's Z-axis, Tipper, electromagnetics. And basically use the same sources. It's just the natural fields of the Earth, but you measure a vertical component of a magnetic field with your helicopter, and you use a ratio of that with a reference field, a magnetic field over here. And that actually gives you enough information to tell you something about the electrical conductivity of the Earth. So that's a natural source. It's ZTEM. Anybody heard of ZTEM? 1 or 2 or 3, 4. Yeah, okay. Anyway, we have a little bit of background on that to talk about. Induced polarization, we did present pretty much the material that formed the basis. Didn't show an example with respect to the waste dumps. Oh, and then there's a couple of other things that we have. I knew we weren't going to get time to show them yesterday, but again, that is the possibility for today. If you have a grounded source in kind of like a traditional horseshoe, so now you've got EM and you've got DC resistivity. So we actually do have an example to show how to take those data at the early times with the induction and use that to get a 3D model. And then you can compare that with what you'd have got with the DC resistivity. So it's just kind of interesting, and it shows how much more information you can get out. One of the big problems, certainly in Australia, but it's perhaps more relegated to the mining industry, is getting rid of the EM coupling. So when you have induced polarization, as I said, you've got this region of conduction that really does play havoc with your data if you're trying to just take your data and interpret them as being IP data. So if you can do something to get rid of that electromagnetic effect, that would be really good. And yeah, basically, we've been doing some work on that, and I think the examples that we have are pretty good. Lastly, I think maybe it kind of came, I touched on it when we did the future, and that was the use of multiphysics. So my group has been working for the last, well, finished now, but for a couple of years on a project that's connected with the kimberlite exploration, so looking for diamonds in the Northwest Territories. And so these are big explosive events that come up, and from airborne geophysics, you can actually get information of what you can do: gravity survey, gradiometry survey, do magnetics, and you can do an EM experiment, all from the air. And we've been able to take those data and for each of the different data sets, invert them in 3D, and thereby recovered a density model, a susceptibility model, a conductivity model, and a chargeability model. And we're able to put all of that together with a classification algorithm to generate what we consider to be different rock units, and then finally translated those to geologic units. And I think that kind of puts sort of the state of the art, of, at least from the groups that we're interacting with, of how to go from multi-geophysical data to something that is actually, that a geologist would really connect with. So that's kind of where we are, and I can talk about any of these things or none of them, which is perfectly fine. The other things that I would like to do today, and the most important for us, is to get some feedback from you, or some discourse from you about the problems that you're working on, and just to kind of discuss it. So what I had asked yesterday, and I hope some people are willing to do this, is just to have a very short talk to 5 minutes, kind of tell us sort of what you're doing, what you'd like to accomplish. Even if it's just asking a question like, well, I've got this problem here. I mean, do you think there's any EM technique, or think about this EM technique? Do you think it works, or why, or why not? Those would be great questions to discuss. And I would put that at kind of like the highest rank of some of the things that we might do today. And then in addition to that, we have a lot of material on SimPeg, or how many people here actually program? Who's a programmer? Almost everybody. What language do you use?
Python.
Pardon me?
Python.
Oh, Python.
Yeah, Python, like that. Yeah, because we use the NCI, the National Computing Infrastructure, the cluster computer.
Mm-hmm.
Yeah, because of license issue, so we try to use open source.
Right.
Everything try to use open source. So Python doesn't need any license. So they all shift into Python from MATLAB, shifting to Python.
Hmm. That actually seems to be quite a common thread we've been to a lot of places. And, people are doing it, can get up with the MATLAB license agreement. And it's fine at the university, and then people at the university, okay, they become really adept in this, right? Then they go to industry and they're kind of, I can't get a MATLAB license, right? So it's challenging. Anybody else who is Okay. MATLAB.
Yeah. Many function C, like Python.
Anyways, oh, sorry.
Also, I was just going to say I use Mathematica, not MATLAB.
Mathematica. Oh, you're a theoretical gal. we know about you. Okay, so Lindsay will open up, talk about SIMPEG, the structure of it, and how it can be used for simulating and inversion. And yeah, we can also use that as an opportunity, since the Jupyter notebooks are programmed in Python. It's an opportunity to kind of take you through a notebook and kind of unravel it a bit and see, okay, what's there, how are they put together. These notebooks, because they're open source, also provide templates for how you might want to structure things. So the more notebooks that we have out there, I think the easier it is for other people to try something out, get on board, and wait a minute, we should change this, or we should change that, or actually I'd like to have something that works in this manner. And I think by getting a large number of these going and getting people interacting as we go around the world, that it'll actually really help make a community. And as I keep saying yesterday, that is the thing that we really want to accomplish. If we can get people talking about electromagnetics, people talking about computational things, and integrating theoretical stuff with simulations and conversions, everybody will be better off. So that's our goal, and so we can take it from there. If there's particular things that people would like to see or to talk about with what I've said up here, let's do that first, then we'll go on to hearing what you have to talk.
Can I just make, this is just a personal suggestion, but I wouldn't mind seeing the Magdalena case study, and then anything that you think would be particularly applicable to the Australian situation, the high conductivity, overburden, things that we might, any examples or advice that would be particularly applicable to Australia would be something of interest to me.
Okay.
For reasons that maybe become more logical
Yeah.
when I talk a little bit about what we're trying to do. So.
Okay, good. We'll do Magdalena. Anybody else got yes?
I think you had a Sam.
Yeah.
Well, we want to work through that.
Physical example, example with different conversions, multi-physics example in Northern Territory in Canada,
Yeah.
where different data were inverted in order to map the accumulate lines. And do you have any examples of EM application to find archaeological objects? Or to archaeology?
No. Probably the closest thing that we have there would be basically using ground penetrating radar.
Yeah.
It's pipes. Maybe think about it. Some of the infrastructure is being archaeological, but I don't know. If there's something wanted to know something about the basis of it, do that. I don't think we have a that would be great. We don't have an archaeological example. It would be nice to do that. Did you know of one?
I know a few actually. In Greece, in the last 5 years, the University of Thessaloniki, I think, is doing a lot of exploration using GPR in order to find all the colosseums and walls. And there's a few successful examples in Serbia as well, finding all the Roman cities.
If you have what you consider to be a really good case history, it doesn't necessarily have to be written by you. If it is, it'd be great. But even if it isn't, if you think it's a really good case history, I'd like to talk to you about it, because what we're trying to do, we're trying to put on our website case histories, but we want case histories that have a really high impact, right? We don't want to have something that's just like mushy. So isolate those that really have a story to tell, so that when people look at it, they go through and say, oh, that's great. You know, EM could really work here, right? I'm gonna try it out. And so we're looking for the success stories. We're looking for, you know, things that just really have a high impact.
Yeah, there's a few things I can suggest that you paper and I point out to, we can discuss that.
That'd be perfect. That'd be perfect. And that actually works for everybody here, because the idea with the case histories, as I told you yesterday, is that some people, that'll be the first thing that they go to. They'll go into GeoSci, and then they'll go to the case histories and see, okay, what do we have? And then they'll look for something that is a problem related to what they're doing. So in your case, it would be archaeology. And then they go to that, and then one of the first things they might see is you know, GPR. Okay, so what's GPR? Well, then you go back to geophysical surveys with GPR survey. In that, it tells you like, okay, this is how you go and, you know, conduct the experiment. This is the data you get. This is what you do. But within that context, there will be some things that we'll talk about, you know, in wave propagation or the fundamental physics of what's going on. That brings you back to one of those 4 fundamental things. So what we're trying to do here is develop a resource that that's really multi-level, that you can kind of go through and, you know, not be too detracted at any particular time. You've got a question, okay, let me answer that question. Now I'm back here, and, you know, this is where your web-based resources allow you to do that. You cannot do that with a book. It's too cumbersome. So that's what we're aiming for. It's a huge project. There's lots of stuff to do, but there's also opportunities for other people to contribute.
It just occurs to me, you will know Sheldon Briner.
Oh, yes.
Yeah, so Sheldon, for those in the room that have ever used a proton magnetometer, you might have used one made by a company called GeoSci.xyz. So Sheldon's company was the one that, well, that was GeoSci.xyz, and when he sold it off to EG&G, he made a fair amount of money, but his hobby is archaeology and using geophysics. So he has a lot of really good examples of using geophysical tools to, specifically in discovery in Mexico, the Olmec, old ancient civilizations, and looking at Mayan and Olmec, OLMEC civilization. So that's his passion, and he's got a lot of good examples. He's put a lot of money into it.
Oh yeah,
so
yeah.
That would be a good source of.
Is he still living?
Oh yeah.
Oh wow.
Well, last email I had from him, he was.
No, I've never met him. But honestly, you know, that handbook that he has for the magnetometer, I mean, that's decades old, and we've used it for ages. Oh,
Yeah, he's still inside. Yeah.
oh, okay.
I'd be interested in hearing about that coupling issue that you talked about yesterday with Equinium, and that stuff we took up the early time and the leaks and anything to do with, I guess, issues that you might find when reporting EM data and stuff that you need to look out for, or whether or not we just report it and plug it into a conversion that's all okay. I'd like to know that kind of thing.
Okay, yeah.
What we should be careful.
Are you concerned about it from the IP part of it?
Not necessarily IP one, but more the EM, airborne EM, ground EM.
Okay, I'll show you a really nice. I can show you a really nice example for the ground EM.
Yeah.
It'll be synthetic, but
That's
it'll give you the idea. We don't have to go through a lot of the details. It'll give you the idea of like, oh, I need to worry about that, and that's stuff that people invariably throw away. And some of that will actually come out a little bit in the Helisam. Okay, well, yeah.
But more, do you have applications for using AEM? Yeah, because of the AEM can be like 300 meters. for some applications, for example, we want to look at more than 300 meters, then we would think to use AEM for the top 300 meters, then might put the rigs for the deeper stuff, then make the whole range. Do we have any examples? We do another section, they do a AEM survey, then our section that's magnitude rigs.
Yeah.
But we haven't put together like from the survey design to inversion all together. We just do separately. The other section did AEM, then we did AMTs, the top 800 meters. But MT would miss out the top maybe 100 meters. Yeah, we have applications actually put these two techniques together. Then get just a full picture from the surface to maybe 1,000 meters or even deeper. Yeah, our groundwater branch, they are thinking to use this technique to map shallow and deeper groundwater.
Right.
Yeah, then that would need two techniques combined together from survey design to the final and the findings.
I have some stuff, but it's not, some of it's not very presentable, but we have one example where, there's control source, EM, that is using, but it's in the marine environment. It's for the Red Sea. We're just putting that together right now. So they're doing marine EM, but it gives you only the top part, and then they use the MT, and then they combine them.
The difficulty for doing the control source
Right.
is we need a licensed operator because of the electrician. We need to get a license to operate the control source in Australia. So which makes difficult.
Because of the landowners or because of some government?
It's a government permitting, yeah.
Sorry,
It's a government permitting. It's different from state to state, but New South Wales especially. You need to have a licensed electrician on any of the.
a licensed electrician.
Yeah, that makes it really hard.
So we haven't done any control source.
Oh, I've not heard of that before. A licensed electrician.
It's mainly New South Wales, but yeah,
It's because you've got the transmitter. You can take the course, Jeremy.
you can take a course to get the license and things, but you do have to actually pass the standard electrician's thing, which is difficult. When I was working for a previous company, we had meetings with guys in New South Wales, and the department got very uncomfortable that there was people putting current into the ground and just put a blanket law on it. So there is licensing issues with control sources. Yeah.
But we have the advantages. We have another section with AEM. Yeah, we just need to collaborate with another section.
Yeah.
But from the very beginning, from the survey side. Yeah.
Do you have data sets? Do you have a data set at this point that has the AEM data and the MT, and you just would like to have some way of combining them?
No, ideally, we have AEM, but not exactly the same location. MT and AEM, not exactly the same.
Okay.
Same location, but in the same area, but not the same location, because they have been done by different sections. So from planning, there's no interaction to blend together.
Right, so that's a really interesting problem. Actually, I think from a technology viewpoint, we're pretty close to being able to really actually have codes that can handle both MT and airborne EM.
Yeah, because groundwater, they are one branch, so they can plan AEM. They actually planning to do AEM right now, Then later on, they will learn empty, or they put them at the planning stage. Once they done EM, then empty is a survey plan can do the same area, same line, maybe the profile. Yeah, so they have the opportunity to do the whole thing. Yeah. So,
well, the question you're talking about is actually totally related to what you're doing too.
Well, they're connected at the hip.
Yeah. So you've got different systems. They see different depths. You want to really combine them.
yeah.
And
And the good thing is they can use AEM data to correct the static state.
Right.
With the static shift, empty always subject to the new surface conductor because the resistivity shifted.
Yeah.
So basically, you need a software joint in practice.
Yeah.
With
There are some
sensitivity, so.
there are software to handle using AEM the time domain data to correct the static shift. Yeah. So we have AEM and empty.
right. That's another discussion. I'm not actually very keen on that approach. That's the way people have traditionally done it. They'll go out and use it. That's what was done for the Iceland project with the ISOR, the Iceland Geological Survey. Traditionally, when they went out to look at MT data, they would also do a central loop packaging sounding, and then use that information to correct for what they call static shifts. The static shifts are only something there, that's just near surface structure, and in many cases, you can actually model that out. And the route where you go and you take some independent survey to try to get some information about that near surface conductivity, and then use that as a constraint is, I think, a much better route to go.
DC could you could use the DC.
Yeah.
It would be interesting to hear if you had experience with not so conventional applications of electromagnetics, like electromagnetic heating for water recovery, and the other is seismic-induced electromagnetic behavior.
Yeah. So the electro or the seismic EM connection. We've not done anything about it. I mean, you've got an expert here, Anton Kepik, who's he did a lot of stuff in the early days. I'm not sure whether he's still working on that. I'm not sure exactly where that field is. So that's seismo-electromagnetics. The other that you're talking about is using EM basically to heat oil, and then no, I don't know. I don't have anything about that, but that sounds like that would be an interesting case history if you have something.
Nowadays, people trying to change their old conventional ways of heating this way to this electromagnetic content because they seem to be more effective. And, I just read a couple of papers, but I've heard anything else about it. Interesting.
Well, I mean, I think these things are great. You just see more and more. That's why I'm so enthusiastic about electromagnetics, because it almost doesn't matter to which problem you turn. There's very often a connection with some electromagnetic survey. So the whole field is so rich with potential applications that it's good. Okay, so now I almost forgot what we were. You have them written down. Who do we do first?
So magnetic colleagues have TKC and EM coupling.
Okay. Before coffee. No? Well, we'll just kind of be short, right? Magdalena, is that in, is it in grounded sources? It's the green. Let's see, where do we put?
Oh, sorry, Doug, it's inductive sources.
Okay.
Slide 62.
Sorry, you think you'd know where your own stuff is, but there's a lot of stuff.
This is just what Doug's pointing out. A lot of the case histories we actually have written up on GeoSci. Not all of them are there, but if you're curious to sort of find out a little more in a little more detail, most of the papers are also linked as well. So you can, the case history that's on GeoSci is meant to be a bit more of an overview, and then the paper is actually what was published in the scientific literature.
Okay. 62. There we go. This case history just came up a few months ago. We saw it was written up in Leading Edge, and we contacted Granda, and she was very happy to have us put this case history up. So the reason that I like it is that this is a well thought out of geophysics in solving an exploration problem. They haven't just said, oh, well, we need to do some geophysics, let's grab this and go ahead and do it. They really thought hard about what they're wanting to do and how they're going to get it. It's very methodical. So I thought that was really good. And the results are good. So just to give you a bit of background, this is in Spain, and it's complex geology, and basically we're looking for ore zones that come up. So these are massive sulfide mineralization. They're steeping, dipping domains, tens of meters across, hundreds of meters along, and is to try to find these, and also if you have found one, try to maybe use the boreholes to try to find more of them, to try to find those that are off hole. In a very simplified form, the resistivities that we really need to worry about, the host rocks have very high resistivities. These around conductivities. So very low conductivities, and the sulfides are really highly conductive bodies. There's also density and susceptibility contrasts that go with them, but we'll just look at conductivities. So here is the kind of targets that they had and the methodology that they use. So if you, in their initial stages to try to find potential targets, they're going to use like a VTEM survey. So that allows you to go over things very, very quickly, cover large areas. So you've got 350 square meters. So that's survey number one. Then they're going to, after having found something, do a Miesela mass experiment. That's going to be single current in a borehole. Talk about that. Then this is the part that I thought was really interesting, because they now want to go onto the into the field, and you've got multiple choices of survey types that you could use. Which one do you use? So let's try them out and see which seems to perform best for this particular kind of target. And they do three of them. They do electrical resistivity, they do a TURAM, surface EM, and a swing ram configuration. And then for off-hole conductors, they're going to do some borehole work. So there's actually quite a bit of stuff going on here. And in fact, this is kind of a nice end slide for the discourse, because we've got airborne time conductor source, mesola mass, that's effectively DC resistivity. ERT is DC resistivity, and then you've got some more time domain EM with surface configurations, and then you've got borehole. So that's a lot of different stuff. So the initial discovery was a BChem survey. So here is the map of the BZ component. As I said, there's 350 square kilometers. The system actually measures dBdz or dBdt, but it can be converted to B. And across, so it's across this line here, and you can see there's this great big anomaly that's sitting up here. That's in the BZ component, and dBdt looks like that. So there's your initial kind of potential discovery that they're going to kind of follow up. So they followed that up. They drilled it. They got a target. So they were successful, and then they want to try to do what's called a mesola mass. How many people know about that? You answered everything. That's good.
I've actually done one of those.
Oh, really?
Yeah.
Oh.
In Nevada. Yeah.
Oh, yeah. What were you putting an electrode into?
It was a sulfide / gold related deposit.
Okay, that's great. Okay, so the mesola mass, for people who don't know. So here's a borehole. It had gone through the vein, so they know where this is, right? So what they want to do is basically do a DC resistivity experiment where they put the A electrode down here. So they put one electrode down here and then another electrode someplace off at the surface. So from yesterday, you now know exactly what's going to happen. So if I put an electrode down here, what's going to happen? Where are the currents going to go? Where are the charges? What are the charges?
Current's going to flow positive in the conductor.
That's-
Positive and negative charge on each side of the conductor.
Oh, you were doing so well to the last sentence. Okay, anybody else?
Will the conductor have a certain charge on the surface of the opposite charge?
Oh, don't make me cry. Okay. Anybody? Okay, what? Remember the sphere? And a current that went in the sphere and then out, okay? So the current, so we had a conductive sphere. The current goes in, and then can you remember which side of charge it was? It was a negative charge as it's going in. So it went from a resistor to a conductor, it was negative. From a conductor to a resistor, and it was a positive charge, right? Okay, that's what we saw yesterday. So now just change that just a little bit. I got a conductor here. I put a current in. Where's the current going to flow? Yeah, it doesn't flow out. It doesn't flow out everywhere, right?
Everywhere.
It's just a big conductor, right? It's just lighting it up. So it's flowing out everywhere. So now, are we going to have positive and negative charge? No. It's just every surface that I look, I got current flowing from conductor to resistor. Oh, it's just positive charge. Good. Positive. Okay, so that means the understanding of this guy is I'm putting a current in here, and now I get this positive charge everywhere. Okay, there. Now you've completely understood the whole essence of what's going on. Because now you could go ahead and put some potential electrodes up here, and you're just going to measure the effect of these positive charges. And if something is dipping way, up here, and it's got some amount of positive charge, you're going to see something. Okay, so that's it. If you do the meso mass survey over that particular vein, you get something that looks like that. If you do a line across here, you get something that looks like that. So just the background half space, you expect to have this dashed line. The actually measurements kind of come out like that. So there's something really going on here. And if you attempted to invert that, you might get some information about the shape or location of it. Okay, so meso mass seems to be done on a regular basis. I haven't heard anybody using it for ages, but they use it, and it's providing them some information. So now they want to do a methodological test, right? And they've got a number of surveys that they could use. And which one do you choose? Well, let's try them out. So they have over the drill hole. So this is the drill hole here. So here's the meso mass result. So they're going to take an ERT line across here. So they're doing DC resistivity across here, collect the data, invert it, and this is the result. It's a bit wonky, but the red is basically resistive. The light colors in here, the lighter yellows and greens, are more conductive. The interesting thing, this is the ore body in here as you're going down, and it is a little bit more conductive in here than it is here, but still it's nowhere near the kind of conductivities of 1 ohm meter that they were anticipating. So these are more like 300 ohm meters. I mean, that's more conductive than this, which might be 1,000, but it makes it kind of subtle. So that just doesn't seem like a particularly good experiment to use. So then they used a TURAM. So if you know what TURAM is, it's a big loop, and then we're going to use that loop to energize your object. And then you add individual time channels. And just the same, remember that sphere I showed you with the airborne EM? Right? And then early times you didn't really see anything, and then a little bit later time, that sphere started to shine out, and then later times it kind of went away. These are just what the results are when you kind of have a body in or do not have the body in. So with the body in, okay, so these are the field measurements. Here's the measurements that come out when you predict what would happen with just about nicely in the TURAM. And similarly, also it showed up in a sling ram. So sling ram, it's kind of like that sort of EM31 type of thing, where you're just basically moving. You've got a loop, but in this case it's a larger loop, and you've got a receiver. So you're just moving that whole thing along this line. And again, you've got a very nice signal over top of that conductor. That was inconclusive. The TURAM provided a strong signal, and the sling ram strong signal of detail, but you can test some. Okay, I'm going to go now. They took that over the whole rest of the property and was actually pretty successful. In one of the holes that they had, just a second. Yeah, so then they were also able to do time domain EM from this from the same hole and go down through that conductive plate. And if you look at the early time channels, you get something like that. So here's the plate, and so you get high responses in dBdt, and in the late time channels, you get actually a crossover in what's going on, just because of how the currents are going in the plate as a function of time. So the borehole was a strong borehole. Measurements were good at finding this guy. But what was really interesting is whether you could use borehole measurements to detect something that's offline. So they had drilled another hole, MA21, and this is what they had. So there's no big peaks in here to say, oh, well, we found a big conductor. But they had drilled it to 320 meters, and just before they kind of quit, starting around 300 meters, the signal started to increase. Question like, okay, what is that? Is that possibly an off-hole conductor? So what they did is, in the second phase, they lengthened that hole. So they went back down again. They drilled from 350 down to 500, and this is the result that they've got here. And now, as they go through, here's the borehole result, and you've got mineralization that's occurring in there. So that was kind of an interesting story. You go through, you do a borehole survey, get something that's kind of interesting. It's intriguing. So maybe lengthen the borehole or drill another one and see. And in this case, it turned out really quite nicely. So I think that's kind of a nice example. It's got a lot of stuff in it. So VTEM was initial discovery. Meso-Lamass was a little bit more in the evaluation phase. Methodological tests, ERT, TURB, SLINGRAM. Both of these time domain systems were perhaps okay. They chose this. And so in the end, they end up doing, putting surface loops like that, and then drilling down and hitting mineralized zones. Yeah, so that's an interesting question. So in the Turan, there's, and this is kind of general survey design. So you've got a plate that you're trying to couple with, right? And there's a question about, okay, where should you put the transmitter? So we've got a big loop transmitter. Where's that kind of optimum placement of the loop, okay, with respect to this object that you're trying to look for? So if I was to ask you that, like, how would you think about that? What are the elements that are sort of important? Kind of thinking about.
Flux, flux,
Right. Yeah. So if you've got, a vertical, if you think your plates are steeply dipping, okay, then, and now I've got so this is my plate, and now I've got my loop over here. First of all, if my loop is sitting right over top, is that going to be a good coupling or not? It's sort of like, no. So I'm actually going to have a hard time seeing this, right? But if my loop is up over here, right, then now I've got fields that are kind of coming in like that. So I've got a lot of phase error too. So very often, and if you go back and talk to the geophysicist who was doing the survey, and trying to find a plate. You kind of think it's over there, and then you're thinking, well, I've got an idea about how deep it might be. So now I'm actually going to put my loop over here so that I get my maximum coupling over there, and kind of. Okay, that's Magdalena. Any questions?
Is Turam still used? It's an ancient technique, or at least the Swedish two-frame sort of technique started a long time ago.
Yeah.
It's still used.
I guess so. They claim. Well, also, in some of these cases, maybe the name stays, but the instrumentation changes a little bit. I really don't know. But yeah, I can't even remember what there's anything specific about what made a Turam, or was it just a loop?
Well, the word is Swedish for two-frame, and it was ABEM, the Swedish company that started it. Yeah, it was a long time. I still remember the gear we had at Stanford. It had a gasoline, and the receiver electronics were really steam driven. They were really
Okay. Yeah. Okay, so heli sound. Yeah.
The whole TDE, what does the whole TDE? The last step, the borehole.
Oh, sorry, I didn't actually explain that, perhaps. But I mean, do you know what a?
White line? Is that the white line load?
No. Okay, sorry. Borehole EM. When you're talking about that, they're basically talking about putting a three-component sensor down. So it's a sensor that would measure, S2 coils. So dBdt in this way and in two orthogonal directions. So it just allows you, again, we've got excitation and we've got measurement, right? So those are the things that give you sensitivity. And now the excitation, that is confined to a loop source here. But if you can measure closer, you're in better shape. So the idea with a borehole measurement is that you put a sensor down, and that'll measure both all three components of that magnetic field, and then you use that to help you.
On the off-hole conductor?
Sure, because suppose you're sitting here, okay, and now you've got some signal, right? So it's coming from someplace, and you've got certain decays that are happening, and you've also got maybe three components. So especially if you only had one component, you could see something and you could model it as being some conductor someplace, but you might not even be able to figure out whether it's on that side of you or on that side, right? But with extra data, or sometimes with an extra hole, you could actually, without having gone through the conductor, you can see, there's got to be something there.
Three directions.
Right, yeah. Okay. Oh, rats. So it was.
It was the one just before.
Oh, it's like 49. Here we go. So we're actually pretty pleased with this. We interacted with GAP Geophysics here, and we're Actually, pretty came data from Mal Kadich at GeoSci.xyz, and we're able to do what I think is the first 3D inversion of the helix snap data. So the area is in central Manitoba, and it's called Lalor Lake, and it's characterized by sort of massive sulfides with steeply dipping veins. So there's a couple of different kinds of mineralization. There's copper lead, and then there's copper gold. They occur in different regions of the pipe. In the end, bottom line is they're basically stringers like this, and the goal is to find them. The challenge is that these guys are really deep. These are like 1,000. This is like 600 meters. This is close to 1 kilometer deep. So if you were in Australia, you'd shake your head because like, there's no way you could do that with all that regolith over top. But this is a different environment. It's actually quite resistive. So you're looking for conductors in a resistor, and that's always a good thing to do. That's interesting. I think I carried my thing away, did I? Because I was doing something.
This thing?
Oh, there we are. Thank you. What would I do though? God, you disaster. Okay, all right. So the volcanics, maybe 1,000 ohmmeters. Sulfides, maybe an ohmmeter. As I said, they're in these kind of stringers. So basically, we're just looking for conductors. So it's an interesting survey. There was Lalor has had many surveys done on it. It's basically a geophysical test site, and I think they actually had a symposium about this, and there were, I think, 13 different types of EM surveys that had been acquired over there. And our goal is still one of these days to invert most of them and see if you can't find a common conductivity model that fits all of the data. But at present, here's a transmitter loop. So it's a couple of kilometers on the side, and they're going to put in a time domain waveform, 7.5 hertz, and use that as your source signal. The receiver is actually going to be a total field magnetometer. And so here's a helicopter, here's the bird, and it's going to fly back and forth along these blue lines and acquire data every about 5 meters, and the line spacing is about 100 meters. So it's pretty dense coverage. But I think the interesting thing about this is that, okay, it's a ground-based transmitter, but you're actually measuring data in the air, and more than that, you're now measuring the total magnetic field. That's very different than what we're going to be measured, what's generally measured with coil sensors, which measure dB/dt. So the fact that you're measuring the total magnetic field means you've got to kind of think, okay, where is all that coming from? Well, first of all, we've got the Earth. So the Earth is giving a magnetic field on here. And if there's any magnetic susceptibility in here, that's going to get, the Earth's going to get magnetized, and that's what you do. There's going to be a magnetic component that you're going to find. That's usually what's done in a mag survey. So you've got the Earth's field, you've got this kind of anomalous field due to the Earth, and then you've got an induced field that is associated with the fact that this is a time-varying magnetic flux that's coming from this. Okay, so that's what you measure. You measure the absolute value of that, so cesium vapor magnetometer. So just the same as we work in an ordinary case with magnetics, you want to subtract out the Earth's field, and that gives you a residual, and that is approximately equal to this BA plus BM, these two guys, projected onto the Earth's field. So this is like standard, standard magnetics, and if you didn't have this term at all, this is what everybody, this dog, do for magnetic data. But now we've got an EM component. But we can take that EM component, or this whole system, and we can change the polarities. So we change the polarities, subtract, and put them together, and that actually gives us a datum that is the transient EM data projected onto the Earth's field. Okay, so it's like doing a survey in which you have only one component of the field. Generally, if people do a survey and they have one component, it'd be like, okay, I'm getting a Z component, or X component, or Y component, right? In here, we're still back to exactly the same thing. We're taking a single component, but it's actually the component in some crazy direction, right? That's it. So what do the data look like? Well, at early times, if you look at the data, you see that there's a big red thing going right across here. It's not connected with the transmitter loop. It seems to be here. It's not occurring over here. At later times, you kind of have diffusing down to something like that. So what's going on? Well, the early times, well, actually, go back. I think it's really
Wow, it's a really big power.
So I'll tell you what we're going to do. So you saw that at late times, it looked like, okay, we're getting kind of coherent signal, and these are high values, so that's what you'd expect if you have a conductor, right? So that's probably pretty good. So what are you going to do? Well, let's first of all just invert the late time data. So we're going to throw away effectively the early time data. We're just going to say, oh, that was contaminated with infrastructure or something, whatever. And we're going to invert just the late time data, the last eight channels. The inversion was actually for us pretty interesting because ordinarily we start these inversions just give me a homogeneous half space and let things go. In the case where you have an inductive source, however, and you're trying to find a confined body, it's actually very difficult to get the inversion to start off with something that has got a little bit of vortex currents. So it needs to have something there infected. You need to have some kind of a warm start. Turns out it doesn't have to be very much, but you need something to get going. If you don't, you're going to end up in some place that's not very geologic. You fit the data. The fitting data is never a problem, right? It's just like, okay, does look weird. Okay, so we need a warm start. There's for people who have, anybody heard of Maxwell? Yeah, so we used Maxwell to get a couple of plates, kind of made them into big blocks. Started that with the inversion, and we ended up with something that looks like this. So there's actually, so this is at a kilometer depth, and we're seeing a conductive packet down here. However, just by inverting those late time data, there is stuff that's happening up at the surface. So there's a kind of a conductive blotch that's going on here, and there's kind of a question about, okay, where's that coming from, and what does it mean? So let's do something that people ordinarily don't do. Let's examine the effect of throwing away those early time data. And so now we're going to take just the early time data, okay? And we're going to invert those, and we end up with a conductivity model that looks like this. And this conductivity model is actually reflective of a power line that's going out there, and also perhaps a little bit of additional infrastructure. So when you're doing an inversion, you don't. Let's suppose you've got early times that are contaminated with some stuff, right? Infrastructure, needing pipes or houses or whatever, right? You don't actually need to fine-grain things down so that you model those things exactly. As long as you get a conductivity model for that near surface that emulates what the effects of those structures are, you're fine, you're good to go. So we can actually work with 50-meter cells in this inversion, kind of representative conductivity that fits those early time data, and now say, okay, there's my conductivity structure. So this is not so different from what you were talking about, right? About getting something that would do, let's say, near surface structure, and but with the AM, and then doing the MT. We're still on the same kind of system, but philosophically and to some extent, we're actually pretty same. So what we're going to do is we're going to take this, we're going to put it in as a reference model and a starting model for the full inversion. So now we take this, and notice actually how all these other, so this was the near surface structure that was obtained by inverting the late time data. So you got all this stuff out here, and it doesn't really, well, there's maybe something up here, but there's a lot of erroneous things or things that we don't think are necessarily there. So now we take that previous model as well as the blocks. So we've got high conductivities in here, we've got our warm start blocks there, and now we invert everything. And now when we do that, all of those other artifacts around here are gone. And we see a couple of things. One is that there's this deep conductive packet. That's good. We've got our near surface infrastructure. But the thing that's really interesting, wow, this is really interesting. That's really neat. Is this vertical structure in there? So there's a conductor. There's a conductor there, which we certainly didn't know about. That was subsequently drilled and found to be mineralized. So the synthesis here was that we're able to get a deep conductive packet. What we got overlaid here is the shell from the drilling. So it looks, it's kind of a little kind of opaque, but that's basically the ore shell from their drilling. And then this little vertical packet up here was recently drilled and found to be mineralized. So I think our take-home messages for that was that the early time data are actually important for constraining the structure and improve the inversion at late time. So we can imagine that for the AEM. And so you've got magnetotelluric data, and you're trying to invert them, right? You don't have really very early, very early times or frequencies, high frequencies. And also, you've got really poor station spacing. Right? So you've got all kinds of things that you really don't know about. But now you come along and you do something that kind of fills that in, and now you use that as the starting point. So that would actually help a lot in the inversion of the magnetotelluric data. And yeah, the warp start was necessary for some deep conductors. Okay. How are we doing? Any questions? I should ask you guys more questions. You're very, very quiet. Okay.
TKC and EM coupling.
TKC was. Where did we put that? Let's go upload. Yeah, so there's the EM. Okie dokie. Okay, I've got a preface, and it has to do with that the time domain data that were flowing were problematic. Problematic IP responses. Nobody knew what IP responses even recognize the data. So consternation. Many of the data tried to kind of figure out what was going on. There was various attempts over the process of a decade or more. But the data were never satisfactorily inverted. We got a hold of the data, I guess about 4 years ago. I threw it out to my group and I said, okay, so let's see what we can do. And there's a lot of data there. There was, in addition to the electromagnetic data, there was also some potential fields. And we thought, okay, as a group, let's parse this out and see if we can, combine all these data sets, get 3D versions of everything, and what we can come up with. We underestimated it, and we had a lot of kind of could have been more productive. Like in hindsight, it's easier to realize like, okay, we could have taken some shorter circuits. So in the end, I think we took close to 3 years with this project, but it resulted in 3 papers that have just been published in interpretation. So I'm very pleased about that. But it was a long process, but it was a great process actually from the point of view of the group, because everybody was kind of communicating on one project. So somebody would throw up something, and everybody's connected with it. Like, oh yeah, well, we know that. So here it is. I'm going to go through the usual 7-step procedure, and then look at the various physical properties and see how we can put things together. So here's our 7 steps. We're going to have a setup. We're going to look at the properties. We're going to do some surveys. There's going to be a number of surveys. For each of those data sets, we're going to do some processing, interpretation, and what we're going to do is gradually build up a geophysical rock model from the various stages of the inversion of geophysical data. So we're going to start off with just the gravity data, and then see, okay, what do I know from that? And then build a rock model from that, and then with the magnetics, and just gradually build it up and make things more complex. So every data set actually helps distinguish that, oh, maybe there's another rock unit here. And then let's see what we can do it. This is diamonds in Northwest Territory. Canada is actually the 3rd producer. And the area of interest is called Tli Kwai Cho. It's hard for me to pronounce, so I'm just going to call it TKC. And it's got 2 kimberlite pipes in it, a DO18 and a DO27. So for people who don't know much about kimberlites, here is basically the idea. So they're explosive, and so carbon in a diamond form is actually quite stable at depths of about 150 kilometers. And if you bring it up fast enough, and if you kind of erupt it in some volcanic explosion, it doesn't have time to change phase, and if it gets up into this low pressure, low temperature region, it'll still remain in the diamond phase. So you get these explosive events up. It gives a number of kimberlites, HK, hypothysal, BK, volcanoplastic, and PK, pyroclastic. So this is the stuff that's deposited. Like everything kind of explodes out and then kind of falls back in, and that's one of the main sources or the areas of diamondiferous rocks. So the exploration challenge, based upon some 1992 data that found a magnomite, they drilled on the magnetics. Basically, it was very poor diamond showing, and so they thought, well, let's take a look, use multi-geophysics. So there's the two things, as I said, there's DO27 and DO18. This is the mag survey, so they had detected this guy at that particular time, drilled it based on that. So I'm not sure exactly where they drilled, but it wasn't overly successful. So we're going to come back and look to see what we can do by using modern geophysics. And here's the really interesting part from my perspective, and that is that time domain experiments were done in this, and this was done with an AeroTEM system, an AeroTEM 1. They flew across here, and the earliest time channels were negative. Now, in the time domain experiment, if you've got any kind of conductive material, you should actually get a positive value. So the fact that they weren't able to get positive values caused some concern to them, and they thought, well, maybe the equipment's not functioning properly. But when it was going across, they were actually okay. So it led to some consternation. So they went back, they made a new system, they reflew it, and now these negative values came out even stronger. So now they're pretty sure that they're there. And about this time, a very great geophysicist, Peter Weidelt from Germany, wrote a paper that showed that if there was any negative values in those transient data, they had to be from induced polarization. No matter what kind of electrical conductivity structure you have, you cannot get a negative transient. So V10 was flown, that produced the same kind of thing. So this is the result. So these blues are negative, and the reds are positive, and clearly there's induced polarization that's coming from it. So our question is that, okay, using only the airborne geophysics, gravity, magnetics, EM, how much information can we extract about a kimberlite complex just by using our 3D techniques? Can we actually make a rock model? Like, let's take a geophysical rock model and use that to talk to the geologists and maybe work together to put some names on things. So what's our physical properties? Overall, they've got a very low density. This HK unit is very susceptible, so it's highly magnetic. And then the VK and the PK, they're kind of kissing cousins. They've got low to moderate susceptibility and moderately high conductivity. So that's it. And all of these are distinguished with the host material, which is the host material is moderately dense, doesn't have any susceptibility, low conductivity, and low chargeability. So what are our surveys? In 1992, there was the DIGEM survey. So that's a that's like the result. It's a frequency domain EM system, and that recorded the magnetics as well as frequency domain EM. So it looks like this. So it's basically just like that result. There was the Falcon system. So that was a gravity gradiometer that was done. That was 2001. The Aerotem-2 was flown in 2003. These are the survey lines that are associated with that. And the VTEM was flown in 2004. Various airborne data. There was some ground data too. There's a NanoTem. And some magnetic data. We're only going to work. So the DIGEM data, so familiar with the 7200 hertz, and you can see how this is really lighting things up. So remember from the low induction number, most things are in the shape of this conductor here and that. The magnetic data, just for reference, kind of showed DO26, didn't have very much for DO18. So we're going to look at this cutout section here. So let's start with potential fields. So here's the gravity gradiometry data. The first thing you see about these is that it definitely marks out two, major anomalies here. And so that's the gravity data, and then here is the VTEM magnetic data. So the DIGEM data, 1992, that's frequency domain, looked like that. The Aerotem, 2003, looked like that. VTEM, that, and the NanoTem looks like that. So we got, that's the ground-based data, but I think it's interesting just to see the consistency here, like, okay, it doesn't matter what I'm doing, right? I'm flying this over, I'm going to see this. So you just constantly see these two pipes. So now we're going to take all those data, we're going to invert them, and Lindsay will take you through a specific tutorial about inversion, and we kind of talked a little bit about this before, so this is just kind of like an intro slide for later this afternoon. But we're going to invert these data in 3D. So the potential fields, first of all, for the density, take the gradiometer data and invert them, get a recovered 3D model. So this is very low density here. This is moderately low density here. And these are cross sections. So A prime is on here, and B prime looks like that. So see, unquestionably, there's low density material, and going to try to make some kind of a rock model. So we'll just first of all isolate anything that has a density that's less than 2.4 grams per cc. So and that gives rise to these two shells here, and there's cross sections of the shell. So that's our first case. That's our first rock model. Susceptibility kappa. Here's the mag. We invert that and we get something that looks like this. So if we go back here, here was the gravity, the low gravity. If we look here, here's that gravity shell, but the magnetic susceptibility is north of that, so it's sitting up here. So we clearly have a couple of different things that are going on, and if we look at the magnetics and the gravity together, we can actually distinguish a couple of major, potentially different regions. First of all, based on density, anything that's less than 0.24 gives you those shells there. For magnetic susceptibility, anything that's greater than 0.0065 is in yellow, and then there's an intermediate. So here, it's still susceptible, but it's low susceptibility. So we're kind of not sure what to do about that, right? Because you could either have a unit that's sort of low, sort of mid susceptibility. It's not zero, but it's not high, right? So it's mid. Okay, if it's all by itself, then it's fine. But if you have something that's high, I mean, it has to grade down to some background. So there is going to be a region in there that has got the same values as this over here. So that presents a little bit of a trickiness to this, but we're just gonna go with that, and so that's going to say that there's basically 3 rock units here and 2 up there. Okay, so that's the result from the potential fields. Right, and what do we know about that for our physical property table? Basically tells us that the overall kimberlite will have a low density. HK has a very high susceptibility, so that 1 unit that we saw here, okay, this guy here, is pretty likely an HK unit at this point, but we're not going to make that call right at this point. And the BK and the PK here have kind of low to moderate susceptibility. So they might be some of those other units that are there. Yes, I think I've actually said this. So this region of high susceptibility, this one that's coming in here is going to be probably an HK unit, and some of these other guys here will probably be either a PK or a BK. We really can't distinguish them, but we're starting to make some progress to getting volumes that might have individual properties. So now let's look at the electromagnetics. So we had all of these different data sets. It was the negatives that are a challenge here. So but we do have a DigEm. So we can actually use the DigEm data to carry out an inversion. It's a bit harder. In fact, this was our stumbling block here for these for DO18. The very earliest time channels were negative, and that kind of really destroyed our ability to extract a conductivity from that. But we were able to get conductivity from the DigEm data. So what we ended up doing was to do the following. So let me go back here. So first of all, just to take the DigEm data and go through the various frequencies. So 56 kilohertz. So that'll be at the surface, or that'd be shallow, right? So you're seeing that you've got a strong conductor here and here, and then as you go deeper, or as you go to lower frequencies, notice how this one decreases. So things are kind of dying out. But actually, there's a strong conductor here at depth for DO27. So there's definitely some interesting things happening, and the 2 pipes are not the same. And in the VTEP data, we also have something that is happening. These are very early times, 130 microseconds, and there's 410 microseconds and 570 microseconds. So the things are changing as a function of time. When we look at the chargeability, there's actually 4 regions here that seem to have negative values and seem to be chargeable. And these are time decay curves, and there's 3 places here, A1, A2, and A3, that never get positive. So they're just always negative. But the only region, there's one in here at A4 that starts positive and then goes negative. So what we're going to do, we need to get a conductivity model. So we're actually going to have to combine both frequency and a time domain model. Got rid of all of the soundings that had a negative, did not have positive values to start with. And then we used the DigEm data, combined those two, and you got a 3D recovered model. So here's our electrical conductivity model. It's big here, moderately big there, and here's the cross section. So that gives us the conductivity, and that allows us to put an extra rock unit in here for the for something that's got a low density, moderate susceptibility, but a high conductivity. Okay, so we're going to build this up. There was a big issue within the community about this conductivity that we're seeing over here, this guy down here, as to whether it's actually the lake sediments or whether it's something that's deeper. What we were able to show is that it was somewhat deeper. So I think that helped satisfy that property. So there's one more physical property, now that's chargeability. And here, so here we come to EM coupling removal. Okay, it's done for an IP, the IP part, but this is what's happening. So to remove the EM coupling, well, basically what we're going to say is that the observations that you made, whatever observation, is equal to the fundamental EM response, which is the response without any chargeability, plus an effect of chargeability. So we're breaking that down into two parts. So that gives us that the IP response, our datum, is the observation that we made. And we're going to subtract from that the EM response that's obtained by taking our 3D conductivity and doing a forward model on that. Okay, does that make sense? So look what happens. I mean, I think this is really dramatic. So here's a 410 microseconds. If you just look at the data, these are the observed data, right? So you can see how it's negative here, positive here, right? So it's confused. If we now take that previous conductivity model that we had, we do a forward modeling on that, so solve Maxwell's equations for the time frame, and then look at 410 microseconds, it looks like this. So the IP data should be the difference between this, and this. So we're going to subtract this, and we end up with that. So this stuff is now negative, which is what we want. The IP data should be negative. We put in here, and this guy we've got completely got rid of the positive. This is your IP response. There's your IP data at 410 microseconds. So now we can invert those. So inverting these is basically a linear inverse problem. There's a whole paper that's been put on with Soggy and I about that. But basically, we take that, we invert that, and we get this 3D chargeability. Okay, so that's going to be our goal. So we're going to do this at 2 times. We're going to do this first at the early time, which was 130 microseconds. So here's our IP data. We invert that, and we get something that's really chargeable up at the north end, at U18, and we get these chargeable bodies here. So we got 1, 2, 3 kind of chargeable bodies that are sitting up there. One of which is coinciding with the pipe, and there's these other 2 guys. If we go to the late time, 410 microseconds, now the whole situation has changed. Where's the chargeability? The chargeability is sitting right down here. So we still see a little bit of this, but basically things have shifted. So something is happening as a function of time. Remember when I was talking about the IP phenomena, and I said, oh, we're going to put like a field across here, so it's going to take time for things to build up, right? And the time that it takes things to build up depends upon what the nature of materials are, various kinds of sulfides or whatever. And similarly, that's going to be what it takes to discharge. So things are happening. These two things are not the same guys. So one can do further analysis on this if you adopt what's called a co-model, and then go ahead and invert for parameters, the tau parameter, which is the decay time, and just a chargeability strength. So you take all the information, and we have a plot a chargeability versus time here. And what we notice is that there's kind of two major partitions. There's a group of rocks over here associated with the A4, right, that have very long time constants and significant chargeability. And then those are differentiated over here. I mean, all have lower time constants. There's some argument perhaps could be made that maybe you could even micromanage these guys and find that there's some differentiation between these rocks. But there's certainly at least two different groups. Two different groups means there's got to be two different rocks. So now we put that in. So now we got 5 elements in here, and we've got 2 that are associated with the IP polarization decay curve. So the red is really long time constant, and the green is kind of smaller time constant. So that gives us rock units 4 and 5. So we can put all this stuff together. We've got now a table of rocks from 1 to 5, including the background. And each of them, you can see, has got some distinct of density, susceptibility, chargeability at time. So you can put all of that then into this classification algorithm and get out your final rock model. And we do that, and this is now what we get from geophysics. Okay, so all we have identified here is rock 0, that's the background. 2, 3, 4, 5 different rock units up there. So we've got extent of the volumes and the fact that they are different. This area has been drilled, geologically logged, and from the drilling, we're able to generate a geologic log in which we've got these colors here. So the green here is what's called the PK unit. That's the guy that's really important. He's the one that's diamondiferous, actually. And then the VK is sitting up here. The XVK is sitting up here, and the HK is in the yellow. So we see we've actually got kind of a nice correspondence here, particularly between the HK units and the VK units and the PK units. We got a purple here versus a blue and a red, but actually these guys are the same thing. These are all kind of volcanoclastic kimberlites, and that's an XVK. So this is a VK, this is an XVK, they call it a different thing. So I think it's a tremendous success, the fact that they're able to go from these airborne data, generate a rock model that actually has correspondence with that. So the point that we wanted to press home to geologists, explorationists for this is that, okay, suppose you got that. What else do you need? We just got rocks 1, 2, 3, 4, 5, right? But the idea is that if we, sorry, I forgot to show you this one. So here was also the 3D comparison with the geophysics and the drilling. So again, you can see now the correspondence in 3D. So it's actually very nice. I got a bit ahead of myself, but anyway, that was basically our synthesis as far as the different rock units, and what we wanted to really carry out from with respect to talking to the geologists is that okay, we've got this geophysical rock unit. This is what you guys have got. But really, if we had taken this and we were able to put down like 2 drill holes here, if we were able to log get a geologic log, that would identify some rock units and provide some structural constraints. And a geophysical log that could provide some bound constraints, then I think we could even redo the process and be even better. So the fact that we're able to do so much with basically blind inversion and put things together, I think is really, that's really hopeful that we can work here in a longer time. And I think these are the kinds of images that the geologists would really like to see. Yeah, okay. So it has a little bit of the EM company. Yeah.
I just have a question. So is not measured on the samples from drill holes?
Yes, actually, it is. We still have a major program that is kind of looking at that. So we've managed to get core and look at some of the petrophysical results. So we've got density, susceptibility, conductivity, and chargeability. And we're kind of working on a post example for this, where we want to take those lab measurements and see what kind of correspondence we can make with the chargeability that we're getting.
Do you think that using technical constraints will improve your version results further?
We don't know. I think probably the ones that will really make an impact actually would be a geology log that goes. So if you had one borehole that went right through that PK unit, because that's the one that's really of interest this time here first, to see if that was geologically logged so that we knew what the outer boundary was. Finding the boundaries of depth is really tough for geophysics. That's really hard. So if we could place that, have a structural constraint on that, and at the same time have some idea about maybe what the effect of compaction is on the physical properties as you're going down, I think that would actually make a big difference. I think we had a couple of drill holes put in there. It would probably greatly improve.
Doug, I noticed in one of the slides further back, the model for inversion of the magnetic data was discussed. There was a little a footnote at the bottom that said that remnants was included in the model, which is something that's not often done. Did that turn out to be important in this case, the remnant magnetization?
It was moderately important. It improved things. So what was done there, we've been working a lot on inverting magnetic data and using incorporating remnants with that. So we've got basically magnetic vector inversion codes that will tell us something about the magnetization, magnetization strength. And what the incorporation of the remnants did, it changed the sort of orientation of the pipe. If you just did the magnetics and you inverted that, and there was sort of, it looked like the pipe was coming in at some kind of angle. And then we incorporated magnetic remnants and then looked at things again, it came up much more vertical. So it wasn't dramatic, but I think at some kind of level where people are really interested in details, those things may have been important.
Are these pretty young, the actual age of the emplacement of the timberline? It's easier to
somehow I think why do I think 60 million years?
That sounds about right.
That
sounds Cretaceous to everything. Right. Because that makes it easier to estimate whether it's normal or reversed. Then you really have, because if you didn't know the age, it could be anything.
Right. Yeah.
I I've seen that you have inverted your magnetic and gravity data separately.
Yeah.
Have you considered using joint conversion, and do you think it changes in this example?
We did invert them individually. I'm not sure what the connection necessarily would be between the gravity and the magnetics. We've got a couple of different units there. I don't know. Yeah, we've not done that, and we actually don't have a particular routine that does this easily.
Better to do reference model, a gravity model, fit in, and density model. Put the gravity density model as reference model to fit in magnetic model. Like reference each other.
Yeah. We've done that a number of times. Yeah, so I would refer that as cooperative inversion as opposed to joint inversion. But actually, that's an interesting thing too. Like, okay, what do people actually mean by joint inversion? So
Joint, I think that's the objective function need to be linked together. A cooperative model is just as a reference model, reference each other. Yeah, same seismic and gravity model, they reference each other. And Curtin University, they then seismagnetic anti model reference each other. They actually coded the model together. Yeah, it's like just run the model. This output from this iteration goes to the magnetic model, then magnetic output, and goes to the seismic model. Yeah, they coding together. Cooperative, still cooperative model.
Well, I mean, this is it. I mean, you're trying somehow to get some information that's consistent with everything you know. And yeah, the challenge is sometimes knowing how things are connected. It's the same in mineral exploration. Sometimes you're looking for a body that should be both conductive and chargeable. That's great. But sometimes, there's a body that's conductive and chargeability is actually associated with, the boundary of the body or something like that. And if you try to be too heavy-handed on these things, then you can actually force yourself to a wrong conclusion. So that's not good. Okay, but so I think we have one more. So why don't we have a quick break? Let's have some coffee and stretch our legs, and then come back. I'll do that. And then, how many people are willing to talk about what they're going to do? So Mike, 2. That's 2 already. 3. Anybody else?
Well, anything remote that I've done with EM is starting the application to archaeology. It's not completely my work.
That's fine.
So I'll just briefly just point out a few pictures and paper and co-authors, but also have to just warn you that I have complete information regarding GPR that was used in this particular case. I can talk more about magnetic and maybe even gravity data, but not about EM. But it's a good reference if you want to contact the lead author on the paper in order to use this as a case study.
Perfect. Okay, let's grab some.
I remember a story some time ago about, I think it was Diavik. Anyway, the original discovery, one of the original discoveries of magnetic. A lot of other companies wanted to use one of those discoveries as sort of a calibration. So they were flying a lot of things over that. And De Beers or something like that actually installed a person in a tent or somewhere nearby, somewhere in northern Canada, with the generator and a loop, so that when he heard a helicopter on the horizon, they would turn it on and basically mask. That was basically subverting the Have you heard that story?
No, I haven't, but I can imagine. It's so un-Canadian. Oh.
Well, beards.
Yeah. That's right. That's right.
Yeah, to download the video, because that will bring in, that'll give you also a whole different.
Well, we see that too. There's a big job manager to make sure that.
Oh, the businesses.
Yeah, see,
Yes.
So that'll help.
by knowing what the signal was like.
Yeah,
The signal was like, dialed by. So what they did was, we have this, and we don't want people to learn how we discovered this. And we're in sea already. And you can't stop anybody from flying overhead, but what you can do is basically stop something. It's basically not disinformation, but it's like, radio Free Europe, the Americans broadcast short-wave bands in Europe. And your guys would jam transmissions so that the Russians would jam transmissions. So they couldn't hear the American broadcast. Probably we probably jammed the Russian. Sometimes we don't fly. It's been taking it. Yeah, it's it. You always go down.
Yeah, but that's very constant. Because it's same thing, yeah. Well, you just deep it, if you just dig up, then
I wasn't very that close.
Yeah, it's funny.
I think it's just the mindset, just feeling this. But it's impossible to change that, unless geologists don't just control, it's the only way to change it. Geologists lose their power in companies, which is permanent. But that's where the problem is. A lot of people hire, geologists that don't feel like doing things, it's like continues. But we just want to get it sort of better. Yeah. Yeah, it's a secret, quite a few the recent ones. Yeah. Yeah, that's good. Well, it's quite other than that cost of it. That makes sense.
You know.
Yeah, so you just.
Yeah, because you know, it's hard people really. That's how it's right? But then it's quite a good. Yeah.
Okay.
I just love to
I can see it's flat.
People are always a little reluctant.
Yeah, actually, it's lots of papers.
They only just do drill bolts. So rather than do
That was interesting. What we just came from.
I see a lot of false positives and stuff.
And one problem that I had back in there. So I think because we're in back to that. So yes, okay, yes. And so it's hard. So that's things that it's been a while since I've been on station, but I've been to that's one of the things that is kind of so that could be Air Force. And that makes you yeah, that's where. Yeah, especially.
Yeah, exactly. No reference.
And all of they really don't understand.
Yeah, GeoMicro, there's both actually, so it's really, actually, I'm not expecting to want to see things right there, exactly sure what they're, otherwise actually, once the start to progress, if we actually have relationships, like a whole thing, then it's a new organization, which is really cool. So, because that's kind of interesting, right? You get,
Yeah.
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 And the also is really, because it is size of the park.
Yeah.
So you can get things like that. Well,
That's hard. Respiration.
Well, it's a pictures.
Because that's what I was thinking.
That's a big one.
Yeah, I mean, it depends on, I guess, sort of how the operating costs.
Oh, no, we didn't. It would be great, but it's different, we don't have.
Geophysics,
Well, there's, and I was just, I'm looking at some of the areas when you have to see where the other than just. Yeah. Which is not an unrealistic system, but then I was going to use oversupplies at the moment there's a bit of discrepancy. This is saying that's No, this is completely separate. It's not coming out grants.
Let's go.
Async. I got a one of the research. With the anyway.
No, we don't. I was very
Watch it for a month or whatever it is.
And hope that all the soundings are okay. So I think Mike's going to get a deal with
There was some years ago, the US built basically translation. You can make a case and say, okay, we need 500 receivers. Yeah. Pack up all the executives all around the world. You have to ensure you pay the insurance, but you don't have to pay for it. Size of it. So it's the very so you have to buy it.
Collaboration in the Oregon State zone. So it's zone RX. Oh, and sorry, then they have 25 long period MT and swim so they basically are.
Is it easiest just to get them up on like a USB and we do it on your computer? Yeah, I think that's. So we'll just do. Do you want to just? Because I can pass around a USB. Yeah. Oh, okay. So it is an EM coupling talks. That's what we're looking for? No, I think we'll just look for the synthetic that we have. Oh, sure. Yeah. That was the sources. Oh, yeah, that's right. Whoops, what happened to him? Did you do it right? Oh, with that, okay. There we go. Or actually, no, we should probably. Did you want to see some details about the EM decoupling or some use of how EM coupling kind of comes into the data and how it could be used?
Yes, and that would be good. Yeah.
Okay, then I'll do that. I think that's really something. If there's other issues about EM coupling that you'd be interested in, I've got some other stuff. I know we've got a lot of things. I really want to get to your talks. So much easier. So much easier. Okay, so I've kind of illustrated this before, but I'd like to look at it again. So here's what we ordinarily have for our DC resistivity, and what I'd like to do now is to talk about what actually happens with this problem and the effects of the EM signal, which is the EM signal on your data, and the fact that it's generally thrown away is actually really useful. So if I have a grounded transmitter that looks like this, then there's going to be a lot of induction that is going to be happening in the ground. It's coming from these wires. And that's going to be the thing that we're going to be interested in. So we've got DC resistivity, we're going to turn the current off, and the moment that we turn on them, we've got all of that EM stuff that we were talking about yesterday, which in these cases is generally considered as what's called a gradient array. So again, we talked about that briefly yesterday. Mentioned a lot of these. Some of them might go by quickly. So we have an A electrode and a B electrode, but the current is going around this loop. There's 4 bodies in here. This one's highly conductive, moderately conductive, that's resistive, and that's neutral. It's the same as the background. And there's cross sections. So we're going to look at time domain data from 1 to 600 milliseconds. And if you look at the DC data, then we get, here's the potentials. So you can see this from, this is the absolute potentials. You can see this from the work that we had yesterday. So they're very high at the electrodes, and then they decrease. So that doesn't tell you very much, but if you convert to apparent conductivity, you see there's a big conductor here, a smaller conductor here, and maybe that's even more because there's resistance. The off-time data, however, when in a time domain experiment, look like this. So notice that you've got this high values that are sitting right near the surface. So from what we did yesterday, you can tell, well, oh, that's the effect of the wire coming through. As that now starts to propagate through, kind of contorts around because there's a conductive object there. 80 milliseconds, it looks like this, 130 milliseconds, it looks like that. So you got 4 snapshots at 4 different times of what the magnetic field is looking like. Sorry. So in the off-time data, if we look at A curves at these different A1, A2, A3 are the interesting ones. If you just have a block, you just get a block. So if you just have the half space, you get the blue line. If you have also the block, you get the black line. So you can see that there's a significant offset. So that's the biggest conductor. The sort of moderate conductor looks like this. So there's still significant difference, and the resistor, you really don't see very much except at early times. So what's generally done, you do the DC resistivity inversion. So you take the DC data and you go ahead and you invert them. An important thing here is that you basically got, it's just gradient data, so you've got only one transmitter. So that doesn't give you depth of penetration, particularly. Well, it doesn't give you depth. It's kind of like a mag survey or a gravity survey. This is more like from an understanding perspective, it's more like a potential field to fit something, conductivity structure that's really kind of right at the surface. So you need to put in a depth weighting in. But if you do that, you get out something that looks like this. So you get conductors, big conductor here, smaller conductor there, and a resistor there, and there's the cross sections. So that's what's standard. If we, however, take those data and invert them with an electromagnetic signal, so now we say, oh, this is a full EM problem. Now we're going invert depth weighting. We've got multiple time channels, and you get a large conductivity here, smaller there, and so that's fitting these for a time channel. So if we're to look at the conductivity model, the true one is like this. The result that comes out from DC resistivity looks like this, and the EM inversion looks like this. So, I mean, the DC resistivity is doing, you know, a good job, but the EM has got a lot of data information in it, and it's actually picked out a nicer copy. I think that was picked up because, again, now as people are collecting data and they're trying to get find out what that conductivity structure is with the DC, you know, you're always turning that system off. If you measure early enough, you get enough time channels, you've actually got data there that is complementary to what your DC data is. And yeah, having both of them and inverting them together or individually is just a really great idea. So, okay, so I'm not sure if that really answers your question. We can talk more about coupling. So now on to some stuff that's really interesting, an opportunity to listen to. So we've got, I guess, we have a USB stick. Maybe we could put around her. Who is going to? Are you going to?
I have some slides I can just. I brought them.
Oh, okay.
If you're willing, you are attached the
Video.
yeah.
Oh yeah, that's
Yeah, if that's all right. And then he's just screen sharing. So if you have a little USB.
I probably shouldn't do that with this one because I'll talk.
No problem.
But other people. What do you want?
So how does everybody, what did you bring? Or how do you have stuff that we can show on your computer?
Yeah, any order preference?
Ladies first.
Yeah, fine. Yeah. Well, it's great. Perfect.
Yeah, that's awesome. And then I just press the arrows to go. My name's Sasha. I think both know about it. Capricorn is within 6 incredibly the center. And so the regulars can get to the order of 100 to 300 in some areas, and also because of a lack of understanding of the local basin mythologies within different regions of the Capricorn region. So, trying to overcome this, massive Tempest survey was Tempest airborne survey was done across the whole region at 5 kilometre line spacing. In order to rapidly interpret this, most of the airborne data has been inverted with the GeoSci.xyz label. So this is a 1D airborne inversion code, which has been quite good for most of the inversions. However, we do know that there are some inherent limitations when it comes to using 1D airborne inversion codes. So something that when my supervisor and I discussed when we first started looking at this information was how best are we going to be able to actually interpret, so maybe some of the basement geology, or maybe some of the actual basin lithologies. Can we use this Tempest airborne EM data for more than just looking at the regolith? And what kind of challenges might we expect when we say have some dipping contacts between a conductive unit that either might be an undulating regolith layer, or it might be just a dipping conductive basin lithology that's in contact with an underlying resistive unit, like resistive basin lithology? And what kind of depth of investigation are we going to expect from this data? So what can we get out of it since we have it? So all I did was set up some simple forward modelling scenarios. So first, so really simple forward modelling scenarios. First one, to try and understand the dipping contact scenario, I just set up a simple dipping contact. This grey region here is a 100 ohm meter moderately conductive basin lithology, I guess you can think about it. And that's in dipping contact with the underlying resistive unit, which is at 1000 ohm meters. So I did a forward model of that using the CSI origin and modelling code, and then just inverted it with the 1D inversion code that we've been using in the Capricorn origin to try and see what kind of results we're going to get from that. So I just used a whole bunch of arbitrary reference models. So they were just based on the assumption that there was limited knowledge of the subsurface, because realistically there's very few drill holes in the Capricorn, and we do have limited knowledge of the subsurface. We know the regulars can be in the order of thick, but we don't have good constraint on lithologies throughout the whole in the different basins. So these two are just first column. This is flying from where it starts off really thin, and then the dipping basin lithology gets thicker. I guess you can say the east or the end of the profile. And where there's like less than 20 or 25 degree inversion, does a pretty good job at resolving the dip of that contact. However, once you start to get steeper, so you're getting great, you start to be able to resolve that dip in contact. If you put the exact locations, obviously, along each of these stations, you can resolve every contact. However, we don't have that kind of information in the Capricorn origin to be able to do an inversion like that in the Capricorn and try and obtain that kind of result from the dipping features. One interesting thing with these dipping contact models was complex region here as you're flying across opposite directions. So flight is going from this thicker, more conductive region into a very thin conductor on top of our resistor, and this complexity isn't an issue because we're not in conductor into a thicker conductor, and that's just attributed to the fact of the distance and separation between where you've got all your Tempest on your system and the resistor at the back. So as you're going into a more conductive region, you start to get this conductive artifact, whereas going from a more conductive into a less region, that artifact isn't come up in the inversion. At this contact, this inflection here. So then, to make it a little bit more realistic, we have some conductive regolith over the top of this. So 10 ohm meters and 30 ohm meters to see what would happen, whether or not we could have dipping basin lithology that we might be interested in, and obviously we get a result that's closer to a laid Earth response because our inversion is trying to resolve that kind of feature. So where we 5 degree contact or 20-25 degree contact here, response where we've got 10 ohm meters or less, where you've got a 30 ohm meter regolith, we're kind of resolving that feature, so we can identify, we know the complexity that's being resolved is the result of this dipping contact, but we can't actually accurately resolve that dipping feature. So it's been quite useful for some of the people that are doing some of the interpretation from the city inversions within the Capricorn, because the geologists were quite looking at a lot of lines over all the that we have to do features that we've got. So next thing I did was, again, some other synthetic scenarios looking at depth of investigation. So it was a simple 4-layer model where I had a resistive host of 1000 ohm meters, that's in purple in these little block models here. And then within that host rock, I had a 1 ohm meter conductive unit that was 100 meters thick, so it's quite thick. And then over the top, I've got, so I varied the resistivity and I varied the thickness of that regolith. So I have a look at whether or not we can identify this conductive feature within the Capricorn. So I did heat these models, like thousands and thousands of these models. So I found a good way to try and kind of summarize this data was to not only look at the result in conjunction with the original model and make sure to see whether or not there was any discrepancy between whether the inversion resolved the thickness accurately or the depth beneath. Also to plot up the misfits. So these coloured charts represent the phi-d error or the misfit as a result of the inversion. So where it's red, it's really a really high misfit, on the order of 100. So that tells us the reference model that I've used probably not resolving some of these models, and where it's blue, it's in the order of like 0 to 10, so we get a little bit more of an accurate result. It's not. I found that it wasn't best to solely base your conclusions just on the phi-d error, because in this scenario here, where we've got 100 meter regolith and it's only 10 meters thick, it looks at all the reference models that I've used. These reference models, by the way, again, are just arbitrary reference models that I've chosen based on limited knowledge of what the true model might be. Looks as though we might have investigation all the way to about 1 kilometre below the surface. However, once you start to get to this region and you have a look at the original models, it's really, while it's solving the inversion, we get a good misfit, not accurately resolving the things that we're resolving the depth of the conductor, and we're not accurately resolving the thickness of the regolith either. So overall, we got probably a maximum where you've got 10 metre thick regolith and about 350 metres. But then once you start to 50 or 100 metres, and it's definitely less than like, which is generally the case in the Capricorn, actually is only limited to about 200 to 250 metres below the surface. So realistically, the airborne EM is only really useful in this area to try and find some of that regolith. These in this airborne EM one that I'm showing here, to try and interpret the thickness, the depth of some of these conductors is really unrealistic. They may very well exist. Anything about where, like, what depth they are or what the thickness is for these units. And then, so the rest of my project is going to involve some of the airborne EM data, and then also some ground EM. So we haven't got any ground EM as ground EM, but we do have some ground soundings at the MT data. So I thought I'd have a look at some of those ground soundings and see whether or not we can do some simple layered earth inversions, 2, 3, 4 layers, and have a look and give us an idea of what the structure of the earth might be underneath. So of the thickness and conductivity variations of the new surface layers, and then use that to direct some of the airborne EM inversions that are next to the ground. The ground green. This green line is the airborne EM lines, and these stations here are the ground EM stations that we have. The problem was, a lot of the ground EM stations were really weird, so there were a lot of like negative and hugely positive results at the start of the early time, and it was mostly the later time decays that seemed to be okay. So I can use those to invert. However, it probably won't give us much more information later. Of the regolith, maybe something underneath. So given that that wasn't the best, and I probably would be able to achieve a lot out of that data, we're going to do some MT and AMT surveys that are around some of the conductive lithologies that are of interest. So this airborne EM line that I showed before, located just here, up in this part of the Capricorn origin. So it's in the southeastern part of the Capricorn. So this is the Capricorn just here. And there's a conductive unit known as the Johnson Camp Formation, and it's a pyritic black shale with lots of graphite in it, and it's really conductive. Over here in this green basin is a unit called the Carolina Formation that's been mapped, and that's also got some graphitic pyritic black shales in it. And at the moment, it's unsure whether or not that's actually the same unit as the Johnson Camp Formation, which is interfingered with this different basin here, or whether it's actually a separate unit. So we're going to try and use the AMT and some coincident MT lines to see whether or not we can distinguish that Carolina Formation, that conductive unit in this region beneath regolith, and whether or not we can make any connection between this coincident line and this coincident line up here. And that's all I have to show. Any questions, suggestions?
Are you going to use some magnetic ground data?
Yeah, so I did actually a while back, have a look at mag and grav, but because, so these stations are 5 kilometers apart, and we could do like a massive 3D inversion, but the cells are going to be massive, right? So, and then that might be okay to look at in conjunction with the mag and gravity, but the stuff that I was doing on kind of like the local scale, looking at the basin lithologies, the mag and gravity is just on too big a scale to even compare. Like the mag shows up a lot of protonic like structures and sort of some of the basement Archean rocks, but it doesn't really show much of a difference between things in like the top, say, 500 meters of the surface. Like it just isn't really comparable. So if you had to look at the basin stuff, it kind of stuck with just looking at kind of 2D or 1D soundings along each of these EM lines and seeing whether or not you can interpret things along each of those lines and maybe connecting them through.
Once that you were looking to where you could resolve the slope, you had basement lines. Was that 1,000 ohm meters?
Yeah, 1,000 ohm meters. So
it's the gravity of the magnetics, like the gravity set through.
The gravity was even wider spacing. I think it was like 400 meter line spacing, and the gravity you can distinguish between different bases, but when you have a look on the like at the local scale, it just really wasn't seeing some of those features, because I based these actually initially some of these different ideas on some of the measurements that I took along this drill hole here. So this purple blue lithology is actually the Deuterina formation, which is a really silicic, really resistive region. So I based these models on the assumption that we've got a lithology underneath, probably not the basement, it's more likely to detect the basement, but a resistive lithology that we see in the southeastern basins, and then something more conductive.
Are you going to do 2D or 1D stick and the MT survey you can do?
I don't know yet. It depends on
like a transect.
Yeah. So far, the reason these white lines here, these white dots, this is actually already being done by Samfire. So I was just going to do a coincident MT line that goes through this drill hole, which is also to coincide with that AMT. We can see a little bit further through this really conductive stuff. But in terms of like the actual survey design and what we're going to do, we haven't really looked at that yet, because I think it's going to be money dependent on how much I can actually put into this. Yeah.
So what is the regional strike in that one already done this way, which means the strike this way?
Yep. So yeah, this one. So I'm not sure why DeGrasse decided to do a T survey this way. But yeah, and they've also got this line here, and I'm not sure why they've gone that way as well. Actually, I was talking to Perla about these AMT lighting inversions or 3D inversions on these. 3D. Yeah. I'm not sure. One of them might be wrong. One of the directions. Yeah. Yeah. So we're not really sure at the moment how they've done these inversions and why they've decided to go across in two different directions. But at the moment, I've decided to do the coincident MT in line with this drill hole, so we can compare it with the airborne EM that we have and the drill hole here. And the direction of this here is to go across strike and also intersect a couple of drill holes, which are actually underneath these dots that you can't see. So because there's actually downhole EM on some of those drill holes, and I can also do some petrophysics on that as well to have a look. I'm not sure. I'm assuming it's a concentric loop around EM. The data files that I have are really like all over the place. It doesn't really tell you like how many channels that you listen for, and it looks like the later channels. So I think it was supposed to be like 173 channels, but I've only got like the first 73, and then on that like the first 10 are really all over the place and up and down. So I've only got like the middle bit of the decay. So I don't really know. Yeah, I don't have the data, but I thought maybe I could extract something out of it and still try and use it. So, but it looks as though they did do. They're still recording in like the off-ramp part of, and so the first part is all a bit all over the place, but then you get kind of like a normal decay at the end. But it's really unfortunate that I don't have the other half, because that's realistically what we're most interested in.
I suppose the
Okay. Raw data, okay. Oh yeah, I can see if I can get a hold of that. Yeah. Yeah. No, that's really interesting. I'll ask and see if I can get a hold of it, but I'm not sure because half the so they have these ones, which is good in my area, but the ones up higher they don't have. They disappeared.
It's going to make it easier for you to find tomorrow today.
That's a good point.
Yeah. Yeah, these ones with the downhole EM. Yeah, so every hole that that Sandfly I've drilled around DeGrasse has all got downhole EM, which is really cool. So I thought it would be a good opportunity to actually do some petrophysics on that as well and have a look at kind of a bit of an upscaling study to see what the differences between that. Yeah.
What did they use for transmitter when they do downhole EM?
Oh, I'm not sure. I haven't actually been to DeGrasse either, so I can't really think of someone there. Does anyone know?
Yeah, it probably uses something. I know I think it looks up because 3200 5.1, probably 100 amps or 200 amps. So around there, single turn. Quality constraint is over 100 amps for just to try and get a little through that.
Thanks. No good mission.
Do you mind if I copy?
Sorry, if I grab a copy of your slides?
Yeah, that's fine.
Cool.
Then you want to use your laptop?
Share. Pause the recording.
Oh, no, that's not it. That's just the
Slides. Right. Just this.
really. Doug is shocking himself.
Yeah, there's something strange about that whole recording. Just a buzz. Sometimes it's like, wow,
Buzz.
that guy.
So we want to get a bigger image than that, don't we? What's going on here? Let's go to I'm trying to find it. Oh, here we are. Displays. Yes. Yeah. There we go. That's about right. There we go. So, Doug, this is really for your benefit mostly, but many of the people in the room are trying to do, but for you and your team, this is mainly your benefit because I'm here with 4 of my students. So the question is, why are we here? And the reason is sure that we take the most, we make the most of an opportunity, fantastic opportunity. So CSIRO has set up a thing called a Deep Earth Imaging Future Science platform. I'll explain what that is in a minute, but it's basically an ambitious project to develop what we generation tools to explore and recover. It's part of a fairly well coordinated effort between government-sponsored effort between several agencies, GeoSci.xyz Australia and CSIRO in particular. But
So I'll walk you through what we're trying to do. Many of you will know a little bit about this. Some of you, of course, are intimately involved with it. But as you all know, Australia looks like that. And it's axiomatic that our next minerals, energy, and water resources will come from much greater depths and from offshore. So the focus is on these three issues: minerals, energy, groundwater, pretty important to the country. We also know that our ability to find these resources, essentially 80% of the country being covered by this thick cover. And about 80% of the country is what we might call, I think we should say, is underexplored. We need to use all the tools we can, from seismic, all the geophysical tools, the mathematical tools, the inversion tools, the AI and machine learning tools, and other kinds of mathematical and inference tools that we can to explore and cover. This project was called Deep Earth Imaging, which it's kind of interesting when you talk to certain people about the deep earth, they mean, you know, one of our advisory panel members is Brian Kennett from ANU, and he said, well, I'm happy to serve as a member of your advisory panel, but I think you've got the name wrong, because if you're only going down a kilometer or something like that, or 2 kilometers, it's not particularly deep. But anyway, deep is deep to some people and shallow. This comes out of a program that now, and many of the people in the room will know about this, maybe not you, Doug, and your colleagues, but about 10 years ago, the Academy of Sciences, people from universities, from Geoscience Australia, from CSIRO, and from industry got together, sponsored by the Academy, and we eventually now called it Uncovered. It's got a lot of legs over the last 6 or 7 years, but it basically says what I'm going to tell you about in terms of the country and the exploration future of the country. Important to Australia. It got considerable government attention. In fact, the resources minister was one of the sponsors of the project, and so two things, but on the part of industry and geological surveys, in this program called Uncovered, and it is beginning to think about putting its money where its mouth is. But the government has already done this in two major ways. The most important, most visible one to date has been for the future program that Geoscience Australia has been funded for, starting about now and going for the next expenditure of about $100 million to do a variety of things, including the numbers, well, not the numbers, but I think an airborne EM survey of essentially the whole country, Tropic of Capricorn, with a few South Australian extensions because of politics and so on. Seismic work, there's drilling work, there's all sorts of other sorts of things that are there. So basically, the government has put a significant resource behind Geoscience Australia. CSIRO has chosen to put its money where its mouth is as well by funding our program, which I'm going to tell you about. Initially for 3 years, it's successful probably for another 3 years, and I'll tell you what the program's about. Agencies are beginning to put more emphasis both in the acquisition of new pre-competitive information to fund the basic research that ideally will capitalize on the expenditures. And so, for example, one of the things we want to do is make sure that we get value from the information that our colleagues in Geoscience Australia and the other efforts will. So this is that's our mission statement, to more precisely and unlock the resource potential. But again, it's focused on those three commodities: minerals, energy, and water. And the reason this could get some political attention is shown here. Over the last decade in the world, about 12 tier 1 discoveries, 4 of which were in Canada. Congratulations in Australia. And this is the kind of thing that helps to get. That's pretty lousy image, actually.
What defines a tier 1 discovery?
Tier 1 is it's an Olympic dam deposit, something like that. In fact, that,
You really have money.
yeah, there's very significant. And so those are the commodities. You can see them here. So there's a couple of them, 1, 2, 3, 4, gold. One happens to be coal, 2 are actually. One's a coking coal, there's a couple of uranium deposits. And that's the situation for Australia. This is the history of Australian discoveries through time, the depth through time, and you can see that, like lots of other countries, the exploration began with people stumbling over things on the ground, then systematic 2D mapping of the surface by. But you can see that most of the discoveries are still quite shallow and have become deeper and deeper through time, becoming deeper than 100 meters by, say, 1950. Of course, is quite deep. If we look at that in a map perspective, you can see large areas where the basement depth is quite deep, large areas essentially no known mineral deposits. However, it's what we want to be able to explore underneath. So a couple of just political statements. Exploration potential is positive. We'd like to think, we hope, fingers are crossed, that we're at the bottom of that cycle. Our exploration expenditures are going to rise by 60% or so over the next 4 years. Another one of our advisory panel members, Chris Pygram, who recently stepped down as Chief Executive of GeoSci.xyz Australia, is talking about the need for example, copper in the future. Essentially, a raison d'etre for the Uncover project is that we need better tools to explore and uncover. Now, we won't be actually in this project that I'm about to describe. We will not be building equipment, but we'll be doing a lot of theoretical work and basic science behind that theory, and try to use as much interesting data and provide tools to work on data provide. So we won't be collecting a lot of data ourselves. Now, I said that we've been given a great opportunity. If we don't squander that opportunity, it's even on a global scale, I think this is a pretty thing that we've been given in terms of resources. So I was funded this program of essentially more than 30 people. So they've asked me, I started this project in January. They've asked me to lead it. So that's me over on the left there. We've hired 4 mid-career people. And the themes you can see them here are electromagnetic and potential field imaging, led by Richard Chopping, late GeoSci Australia. Jörg Hauser in inverse problem solutions. Jörg is a CSIRO employee who's worked for years in electromagnetics and seismics. Luke Peters, data assimilation and expert knowledge inference. He's a hydrogeologist. And then Erdij Seydin, who's recently finished, or will soon finish, I should say, University of West Australia, who's a seismologist. So those are basic themes. Sources to hire 18 early career researchers, 4 of whom are in the room here with us now. We define an early career researcher who is, say, 3 years or less out of their PhD. And also, they've given us the resources to sponsor 9, be mentored by the theme leaders, by the early career scientists as well. So those are the themes. And what are, the term BU here means business units. So CSIRO has a bunch of different business units. There's agriculture, there's minerals, and there's water and land, and so on. So research organization. So we can't pursue everything that we want. We might be interested in doing good science. We obviously want to do good science. But it at least has to be bounded by the domains of business units. That may evolve through time, but at the moment we're sponsored by the energy business unit, the minerals business unit, land and water, and a recently formed business unit called Data 61, which is essentially data science, big data, machine learning, technology part of CSIRO. That will probably evolve through time. investors in the organization, it's probably best to say, well, I view this as a startup company within the larger company. So we've been given venture capital by the CSIRO and the ministers. And by the way, the reason that this is slightly sensitive is, I forgot to say, this is a presentation I gave a couple months ago, so nobody else has seen this, so we probably shouldn't. There's nothing secret in it, but just politically, it's probably better not to do that. Investors know that many of the things we try will fail, and we're expected to fail, but the way I'm trying to arrange this is to put teams of people together who work on a problem for a period of time. If we fail, fine. We fail, we learn from that and move on. Much the sort of fast fail kind of situation you see in Silicon Valley. And that's where, in my own mind, the idea of a startup really is. So it's team-based, rapid turnaround with some stage gates and so on. Failure is allowed. We will produce things that will be useful to Australia from the exploration and discovery. And also, CSIRO has a mandate to essentially pay its own way, at least partly. So we're only half funded by a block grant from government. The other half of CSIRO money comes from we do sometimes in confidence for other organizations. So ideally, the product for Australia, but also good for CSIRO. So it should be designed for uptake by, say, the minerals business unit or the energy or the groundwater business unit. And the last part is pretty important because ideally, although not everything we do has to be commercializable or eventually become. Oh, you're right. Get a shot from this, didn't you? I said the word commercialization.
Yes, sure. This is purely academic.
Where's Mr. Pavlov? Yeah, or Skinner rather. B.F. Skinner. But when we start these projects, we would like to at least we would like to be thinking about, well, what is the commercialization pathway for this? It's not that kind of, but we are thinking with that in mind. So lots of our colleagues have come together ideas. And like I say, I started this project in January, and a lot of people have come together and suggested, well, I think you should do this. And another person suggests, I think you should do that. In some cases, those ideas came out of my CSIRO colleagues because whatever they're doing, of course, is the most important thing that ought to be done, regardless of whether it's strategically important or not. So we've worked over the last 6 months to develop a science plan, which we're now socializing within the organization. But the choice of project for us, and remember, we're covering seismic, magnetics, and rock properties and so on, but also mathematics and data science as well, integrating that together. We had to come up with an agreed upon set of how we would decide to do something or not. Will it have the impact? Is it high quality science? Does it fill a gap in industry's knowledge? Are we the right organization? There are a lot of things that we probably shouldn't do because it's particularly in the energy industries. You know, take a Halliburton or a Schlumberger. You know, we should find the right thing to do where we can make a difference or have a slight competitive advantage. Do we have the right resources? And I should say the talent available at the moment, the talent available is quite amazing. These 18 early career researchers have got over and there's some fantastic talent out there. I wish I could hire more people. And finally, is there commercialization potential? Final slide with pretty pictures in it, but it's basically everybody now knows a lot more than they did about airborne and other types of EM. And I don't know where I stole this image from, but it's an image of science fiction. I stole it off the web somewhere. And when you're explaining things to the board, you know, they told me. So this is a completely data-free presentation because we're just getting started. 4 of the 18 postdocs, well, another few are just arriving months ago. By the end of the year, they'll all be on board. And now we're looking for the PhD students to support. selected Australia. So it's a potential fantastic opportunity, as you'll recognize, Doug, in the academic world that I used to live in, to have the resources to hire one postdoc is good and remarkable, and to get a team together like this, completely and working together, is quite a unique opportunity. So I just wanted to make sure that we're here learning as much as we can, because some of my colleagues probably didn't know much about electromechanics before yesterday, but they know a lot more about, say, mathematics than many of us know. So it's a team of people. There are geophysicians, there are data scientists, there are people like chemists, for example. We're interested in ab initio calculations of how metal ions, together with, say, hydrochloric acid, things form sulfide deposits at high pressures and temperatures. And can we model that using supercomputers, and so on. So it's a very interesting team that will evolve through time, and I'm just delighted to have the opportunity to do it. That's what we're on about. I hope you'll hear more about us.
I'm incredibly envious with a whole bunch of perspectives. Yeah, it's that's actually remarkable.
It really is. I couldn't turn the opportunity down.
I can't imagine, the Canadian government and whatever associations we have in Canada getting together, being on board and supportive of something like this.
Well,
especially like, okay, you don't have to produce, but just bring a whole bunch of guys together. Here's the general problem. Here's the boundary conditions. See what you can do. And if you're successful, that's great. If you're not successful, that's fine. There's no pressure. You don't have to go for funds. You're not running a whole bunch of grant proposals and things like that. Just, I mean, it's kind of like the old Bell Lab type.
Exactly.
Stuff,
That's exactly right, Doug. And last year when I at AGU, Cisco, I was out recruiting scientists there, and I said to a number of my colleagues, I told you, you're doing what? You're going to hire how many people? And so, for example, to put it in perspective, U.S. GeoSci.xyz program called the Mendenhall postdoc, and what we're doing here is bigger than the entire number of people, bigger than the entire USGS Mendenhall program. As a matter of fact, we have a young woman coming from Denver who's just coming out of that Mendenhall project. She did her PhD and then was working for USGS as a postdoc, and she'll be coming to join us. So anyway, it's a fantastic opportunity, so I want to make sure I learn what's the most up-to-date methods and techniques, and also that some of my colleagues who are less experienced in EM, or in seismology or mathematics, but at least they learn what the tools are and what the current state of the art is. So again, thank you for coming to Perth.
Thank you for that.
Yeah. Anyway, that's my story.
With respect to electromagnetics and some engineering things that you have, do you have any comments?
Well, probably the closest to market things that we have will be related to groundwater. But we already have maybe 3, 4, 5 people working in CSIRO on groundwater problems with airborne development. We want to use as much of if we look at a much deeper level, we want to be able to add value to the OSLAM project that's being run by state governments and by Geoscience Australia. And my colleague Richard Chopping will be a great resource there because he's been helping to lead some of that. And it's probably unlikely, but it would be nice to know what kind of things we could glean, what extra things we could glean out of this forthcoming airborne EM survey of Northern Australia. Again, that'll probably be focused mainly on groundwater, but from the presentation I gave you here was mainly focused on minerals. There's the potential, of course, for maybe some work in controlled source EM in the offshore hydrocarbon basins as well. And that's one of the reasons I've been studying what Stephen Constable and his colleagues, and I had the great opportunity a year or so ago to meet at a conference sponsored by EAGE, and I met Len Zerman and talked to him about his work there. And that's probably a fair amount of time in the future, but I would say, so at the deeper end, it'll be magnetotellurics and this Auslan project, where what we can add, and perhaps, for example, problem number one really is we don't have a map, a reliable map of the regolith, even the thickness of regolith for the whole country. So if we could produce, and this is one of the goals of the Uncover program, if we could produce a quality map of just the thickness of regolith, then that changes your whole exploration. You know, it's area reduction, and so, well, that's a kilometer deep. We're not going to bother, at least in this century, worrying about that. So the combination, for example, perhaps of joint or co-inversion or cooperative inversion of MT data, sort of reasonable frequency data to look at the regolith, combined, say, with passive seismics, and looking at the sort of that horizontal vertical ratio from passive seismics to make that kind of a map, and then perhaps put that together with maybe some of the magnetics tools that give you something like depth to basin, things like that. But just to first order a map of regolith thickness for that 80% of the country that's underexplored would be a good tool.
Is the regolith pretty homogeneous, or is it?
No, it's highly heterogeneous. There's transported regolith. There's that's a whole another subset of Cyro's work and GA's work is to map and understand the characteristics of the regolith. It's pretty complex.
But it's irrespective of the complexities. It's always really quite conductive compared to basement.
Always. I think my colleagues in here would know more about that than me. I would say in general it is quite conductive. I'm not sure if it's always conductive. What would you say? No.
Okay. It's hard.
Right.
That's great. I'm really impressed. Yes.
Well,
all
we haven't
right.
done anything yet. You don't have to be impressed, but we haven't done
No,
anything
we've got the vision, right? Well, it looks like you've got one show. You know, I think maybe we can take one picture. Oh, yeah, sure. We were going to do it yesterday, we forgot. But we'll get a picture of the hardcore. Yes. There you go. Great one. Can we do? I'll get somebody to take a picture.
You want to have a good background? It would be a good background.
What's this?